This is CPE 133, Chapter 10 in the Free Range Verilog Foundation Modeling text. We were talking about ripple carry adders, and now added the discussion of signed numbers to that, and now we need to kind of delve back into it. A couple of other issues we need to deal with on this, so let's do it. Yes, the disclaimer, it's there everywhere. You're not going to learn this by watching videos or reading the book. You actually got to just crank through it, work through some examples, and ask questions when you got them. So the issue is with using mathematical operators in Verilog is that they essentially generate hardware. So if I drop down an addition operator, that means the synthesizer is going to provide some type of adder in the hardware that it generates. Now the issue is like, what type of adder is it? I don't know. I don't really know. And you could figure it out if you spent time looking at it. I've just not spent the time looking at it. What you know for sure is that it is going to give you some type of adder one way or another. Now, if you're working some time critical application, it's going to behoove you to know that information. You're going to have to go look at that. But for us, it's just a matter of kind of understanding the details of how this works. Now, the issue that we're dealing with, and it gets kind of confusing, is the notion of signed versus unsigned. Now, the issue is funny because the hardware is stupid, man. It doesn't know whether you're adding unsigned numbers or signed numbers. It just adds the numbers. It does the same type of addition. So this works because of, essentially, in my mind, it's because of the two's complement notation that we represent the negative numbers with. It works great, and I think because it works so great, that's why everyone uses it, because it essentially simplifies some of the hardware. So these are the four rules we're looking at and we're dealing with, and so we'll go over them real fast here. So first of all, the synthesizer is going to look at the expression, both the left-hand and right-hand side of the assignment operator, and look for the operand with the biggest, largest bit width, and it's going to expand all the operands to that bit width, all the operands in the expression. Okay, the second thing is that the synthesizer doesn't know what you're doing. When you add two numbers, two n-bit numbers, you're going to end up with an n plus 1 bit result. The adder doesn't care if you account for that or not, but you, the modeler, has to account for the expansion of bits, and with using some of these operators. The hardware is going to do it for you, at least the operator part, but as far as the width of the result, that's up to you, the designer. So the second thing here is when I need to expand values up relative to the first item here, it expands them based on whether they were declared as signed or unsigned values. So signed values get sign extended, unsigned values, which are essentially not values declared without the signed signed keyword, unsigned values are zero extended. The last rule here is that every expression on the right hand side, the assignment operator needs to be signed in order for the expression to be signed. And what that means is, if I have one value that's unsigned, the synthesizer is going to consider every single value on the right hand side of that assignment operator as unsigned. Even if you declared it as signed, the synthesizer is not going to sign extend those values. Because you have one value that's declared as unsigned, it's going to zero extend all the values, which is potentially problematic. So this is a example. It looks a little bit different than the other example. The previous example worked great. This one actually has a problem in it, but it is a kind of a non-tricky approach of modeling a ripple carry adder. So here's your parameter up here. So if we're looking at this thing, what we're going to see is that Everything's declared as unsigned, which is, technically could be okay. What I'm going to do here is declare this this temporary, like this intermediate value here of a sum, and that's going to hold my sum. What I'm going to do later is divide this temp sum up into the carryout and the sum, but I'm going to do that after I execute this expression within the procedural block, which is the always block. So what this is doing is going to add a plus b plus c. So looks good. I mean, the issue is everything looks happy with this, but there is a problem. The issue is that this is only going to work when I consider a and b as unsigned numbers. If a and b are unsigned numbers, they're declared as unsigned, it's going to work. But if I use this adder and give it a signed value, those signed values are going to be kind of covered by this unsigned designation, and those signed values are going to be 0 extended. Because they're 0 extended, you're probably not going to get the right answer. Okay, so let's a couple of ways to fix this. Probably the easiest way is just declare them as signed, but the point being here, I wanted to show something else in here. So I don't know what that is. So this is one solution for this, and what I'm going to do is I'm going to keep these as unsigned, but what I'm going to do is physically, manually, however you want to put it, sign extend these things, sign extend these operands. So what I'm doing is I'm taking the sign bit of this b variable and extending it 1 bit to the left, which essentially is sign extension. And I'm doing that for a also. And so doing this, this is going to work. It's kind of a tricky little thing here. So the issue is the notion is that all these variables are now going to be n, so it's going to be n plus 1 bits. So this value is n plus 1 bits because of the way I've declared it here. These values will now be n plus 1 bits because I added a value to it. This will be expanded. It's unsigned. It'll be 0 extended to be n plus 1 bits also. And I think that's all I can tell you about this example. We'll have another cool example next. So this one has a problem also. Now what we did, it looks kind of cool because we've declared these inputs as signed, therefore we don't need to do anything kind of manually sign extend, and down here they're going to be sign extended properly. So the issue with this model is the cin was declared as a signed value. So because cin's a signed value, these are all going to be n plus 1 bits here because this is kind of an n plus 1 bits. And what's going to happen here is it's going to need to expand this to n plus 1 bits, and because it's a signed number, it gets expanded to -1 when cin is a 1. So 1 sign extended to n bits becomes all 1s, which is a -1, which is not what we want. We want it to remain 1, like a true 1, like 00001. So this is going to be a problem. A couple fixes for this thing. Probably the easiest fix is just to keep this declared as not as a signed value, just as an unsigned value. And so that works too. A very much similar solution. Once again, it's going to be expanded to either, if 1 is going to be expanded to 00001, 0 of course is going to be expanded to all zeros. So it's 0 extended, and it's going to be right every time. So the other solution to this thing is just tricky, and I throw it in there because I just wanted to, show people that it can be done this way. Okay, so what I'm doing here is I still have cin declared as an unsigned value, but what I'm going to do is stick a 0 in front of it and then magically declare it as a signed value. Now, essentially, I'm using a typecasting here. It's probably not the most intelligent use of a typecasting, but what it does, it's going to take this value right here and consider it a signed value. Once it's a signed value, it sees the leftmost bits as 0, and so when sign extends it, it's actually adding zeros to it. This guarantees that it will always, like CN will always be something like a 0001. By sticking an extra 1 in there, any sign extension will be extra zeros on it. So this is kind of a chunky solution, but you know, it works. So this is like probably the most important slide in the entire chapter, and it's very confusing. And anytime anyone works with two's complement, it gets very confusing. Throw in the rules of Verilog and how they work with signed and unsigned numbers, it gets even more confusing. So I'm trying to sum it up here. So I have an expression here. Okay, so what's going to happen with that expression is when it sees this expression, it's going to look at all 4 of these operands here, see which one is the widest, has the most bits associated with it, and it's going to expand all the operands to that maximum value. Okay, that's one thing. Then it's going to expand them according to the signedness of those numbers. Okay, so we've already seen that, but what's important here, if there's even one unsigned value on the right-hand side of this equation here, it is going to consider all the values as unsigned, even if they are originally declared as signed values. So having one of these being unsigned will force them all to be considered unsigned, which effectively overrides the signedness you put in the declaration. So it's super important you understand that. So anyway, lastly here is this A, or the result here, result operand, is going to have a sign associated with it. Now the sign associated with this operand it's completely separate from this particular equation. The signedness absolutely doesn't matter. Certainly the width matters, but the sign does not matter. This A value will have a sign, but it's only used for sign extension, maybe in some other part of the model that we're not looking at yet. For this particular assignment, the signedness of A simply does not matter. So these are all the rules as I know them. Lots of times you get away without knowing them, but the important thing here is that the hardware is always going to be right. It's always going to do the right thing. It's always going to do the right addition, etc., etc. But the issue is, lots of times you don't know whether that result is valid or not. And so when you're working with signed numbers and unsigned numbers, you could have some type of overflow. So overflow for unsigned numbers is essentially, you can detect it via the carryout. If the carryout is set for unsigned numbers, you had an overflow, and therefore the sum bits are not correct. Now there's working with unsigned numbers, you also look at the carryout. Now the sum is always going to be some value, but the carryout is going to help you decide whether that sum is actually a valid number or not. So, but it's really tricky. You need to understand how all this stuff works so you can correctly verify whether the result of your addition is valid or not. It's always going to be, quote, correct, but what you're wondering is if it's actually valid. In summary, Verilog has a bunch of operators. Anytime you use those operators, it generates hardware. Lots of times, particularly with adders, hardware is stupid. It has no notion of the signedness of numbers. It just does what you tell it to do. There's a bunch of rules Verilog has set out dealing with signed and unsigned numbers, and particularly how those numbers are expanded and how they're dealt with in expressions. So the rules are kind of confusing, but if you read through them a couple of times, they should make sense. And and life should be good after that. So good luck working with signed numbers.